Hello, class. I thought I would do some example on Euclid's algorithm and extended Euclid's algorithm because some notes from the lecture I posted online were not easy to see. And so I would just go over, actually it's the same example. So sorry, I guess I could have chosen a different example and this would make people who actually have seen that one perhaps more interested. All right. So if you haven't seen it, then here it is. It's that part of the last lecture that if you try to watch it offline, it was hard to see. So here's the Euclid's algorithm in a nutshell, right? GCD of AB is in the base case where B divides A, it's just B, and otherwise you recursively run on smaller of the two, because we assume that the first argument is larger than the second, and you shift them one to the left. The next smallest is A mod B. Okay, so let's see how this works for some example, right? 259, 77. When you call this algorithm on 259 and 77, you don't hit this case because 77 does not divide 259. And so you're going to hit this case. So B is 77 and A mod B is 259 mod 77. And that's 28 because of the following equation. Okay. We'll come back to this equation later on. All right. So when you run this algorithm on 7728, then the base case does not happen because 28 does not divide 77. The next recursive call shifts this, so 28 becomes the larger one, and the smaller one is 77 mod 28, okay, which is 21 because of this equation. Okay, so this is 56, 77 minus 56, 21. Okay. So the next run is 28, 21, 28. And when you do this run, do you hit the base case? No, because 21 still does not divide 28. The multiples of 7, you already can see this algorithm returns 7 as the GCD of these two, and therefore GCD of these two, and therefore GCD of these two, right? But technically, we're not true. We're not in the base case yet. So what will the algorithm run? Okay, it will shift to the left. So 21 will be the next larger one. And the next smaller one is 28, not 21, and that's 7 because of this simple equation, right? So the last call is on 21, 7, and now we hit the base case because 7 divides 21. So we return the smaller of the two. We are in this part of the code, right? So it's 7 and it will percolate all the way up. And this is the final answer. Okay, so that's Euclidean algorithm. Okay, and now what about the extended Euclidean algorithm? Okay, so the goal of the extended Euclidean algorithm is to find linear coefficients and S and T such that the inputs, so here was our A, here was our B, right? These are the coefficients of the linear equation S times A plus T times B equals to GCD, which happens to be 7. Okay, so how do you recover these S and T? That's the end goal, finding this S and T pair. Okay, excuse me. So look, the first point is that the trace of this algorithm is the sequence of the B's that are executed, because this A1 is a copy of this B, and A2 is a copy of this, and A3 is a copy of that. So these A's are not interesting, and if you just put this initial one here, then all the B's are these. All right. Now look at the equations 1, 2, 3. The ones you have done, the algorithm has basically made, so that to compute this. These equations can be seen as that the next B down is expressed as a linear combination of the previous two. The next is a linear combination of the previous two. The next linear combination of the previous two, right? So the equation, last equation binds these. The one equation before binds these. The one equation before binds these. And so we move down, right, or up. So if you look, you can look at the equation 3 as saying that the final answer, GCD, is some linear combination of the b's before. What were the b's before? 21 and 28, right? So these are the ones. So that's what this equation is, and it doesn't matter what these coefficients are. The point is that these b's, there's some linear combination that makes 7 into linear combination of b1 and b2. Equation 2 says that this guy is called b2. He is represented as some linear combination including b1 and b0. That's this equation. And equation 1 says that the higher up the chain, b1, which is 28, right? That's b1 is 28, is a linear combination of the first inputs, a and b, right? That a is 259, b is 77. So now you can take these linear combinations and get solve for these. Okay. Let me do it here on this page, right? So you start with the last equation that gave you 7 in terms of the previous b's. And now you use the one equation before, which told you that b2 can be expressed as a linear combination of b and b1. And you just combine the coefficients to now have 7 in terms of b and b1. Now you take the one equation up that express b1 as a linear combination of a and b. You substitute, and then you're rearranging these terms. And boom, these things are the linear coefficients in front of a and b. So let's do this for this particular example, right? So the last equation was like this. Because, okay, here is the trace of the algorithm again. A was 259, B was 77, B1, the first model reduction, was 28. That was 259 mod 77. The next model reduction was 77 mod 28, which was 21. The next model reduction was 28 mod 21, which was 7, and that was it. That there's no further movement because 7 divides 21. So we had these equations. I will copy them here. Equation 3 expressed this guy in terms of these two, and it said 7 is 28 minus 21. Equation 2 expressed this guy in terms of these two as a linear combination of these two, and it said that 21 is 77 minus 2, 28. And equation 1 expressed this guy in terms as a linear combination of these two. And what did it say? It said 28 is 259 minus 377. And these coefficients don't really matter. Whatever they were, you will be able to compute it, right? The point is that these linear equations exist. So let's take them in. 7 is 28, 21. You start from the bottom, from the bottom of these equations. Now you use this one to rewrite 21 as a linear combination of 77 and 28, and that's here. 21 was replaced by this. Now we rearrange the term. It's minus 77. Here's 128 minus 2. So that's plus 2. So that's 3. So you see, this is kind of funny notation. Plus in brackets 3. Why? Because you want to be anal about not messing up these coefficients, okay? Like it's kind of easy to overlook that one of them was with the minus, and then what? Okay, so I'm being careful here. All right. Now 28, I'm now going to use this equation, the final one, that express 28 as a linear combination of my A and B. That's here, that's this move. 28, I replace by this. And then I just group it, right? So 25 and 259 is with coefficient 3. And then what's in front of 77? It's -1 plus 3 times -3. 3 times -3 is -9 plus -1, that's -10. So S and T are 3 and -10. And this is the final. Okay, and now when this is your answer, right? So these are the claimed coefficients. But let's always check that these answers are correct, right? Because there's plus minus everywhere, right? It's easy to make a mistake. So here's the check. Let's see. This was our A and this was our B. So let's see if 3 times our A plus B, which is -10 times, plus -10 times B, is really equals to the GCD, and it is, right? Because, well, 10 times 77 is 770, right? There's a minus sign. And 259 times 3 times 9 is 27, right? So there is a 7 and a 2 carry, right? 3 times 5, 15 with a 2, that's 17. So 7 with a 1 carry, and 6 with a 1 carry is 7, right? So indeed, that's a check. All right. So now suppose somebody asks you a question. What is 77? Sorry, let me refocus the camera. Okay. What is 77 minus in multiplicative inverse of 77 mod 259? Well, it doesn't exist because the GCD of 27 and 259 is not 1. 77 is not prime to the co-prime with the modulus, so it doesn't have any multiplicative inverse, right? It's like your homework last week, where you did multiplications mod 8, and you notice that all the even numbers don't have multiplicative inverses because they're not co-prime with the modulus. Now that's the fate of 77 mod 259. Okay, but let's look at these applications to finding multiplicative inverses, modular inverses. So say somebody asks, what's a multiplicative inverse of 77 mod 258? So what do you have to do? Well, first you have to presumably run Euclidean algorithm to test if these two, if 77 is really coprime with this modulus, right? It was not coprime with 259, but hopefully it is coprime with 258. Well, of course, I mean, this is 7 times 11, and this is not divisible by either 7 or 11, end of story, right? So they are coprime. But because we want to use this, we want to find these, the second goal of the Euclidean algorithm is to run extended version of it, would find these coefficients, which would make this equation true, because we use these equations to find the multiplicative inverses. Okay, if this is an element and this is the modulus, we are going to use one of these things will be the multiplicative inverse of this modulo that. And also we can answer the opposite question, right? If this is a modulus and this is the element, we can also answer that using the same equation. Okay, so let's run this Euclidean algorithm on that. So our inputs are 258 and 77. So we compute 258 mod 77, right? The first move of the Euclidean algorithm. And that happens to be 27 because of this equation. Okay, so the next so the first recursive step would be our previous B, and here is A mod B. Okay, so 258 mod 77 happens to be 27. We're not hitting the base case. So what's the next call? B is the GCD on B, which is 27, and this is A mod B. So 23 is 77 mod 27 because of the following equation. Right, this is 54, right? So, and 77 minus 54, 23. All right. So the next call, this is the B, so I just copy it here. And this is going to be 27 mod 23. Okay, so now the numbers are small, so it becomes easy, right? So 27 mod 23 is 4. So good. Again, 4 does not divide 23, right? You can already see that the GCD of these two is 1, but technically we are not done. 23 mod 4 is 3. This equation holds. All right, so it will be B, which is this, and A mod B. So 23 mod 4, which is 3. And again, base case does not hit. 3 does not divide 4. So we do the modular reduction again. It's B, which is this, and this is A mod B. So 4 mod 3, which is obviously 1. Okay, and now finally we hit the base case. 1 divides 3. Basically, the minute B is 1, that's the base case, right? So this is the answer, right? Which confirms that they're coprime. So 77 does have a multiplicative inverse. And then now let's use these equations, a different example, right? To test, I mean, to find these linear coefficients, S and T. Okay, good. That's what we're doing now. All right, so we start from the bottom. 1 is 4 minus 3. Okay, we have expressed, where is the chain of, where is the trace of this algorithm? It's this. Okay, this is the A, this is the B, which is B0, this is B1, this is B2, this is B3, this is B4, this is B5. Okay, and equation 5 bound, it's really, I can represent it as B5 is some linear relation of B4 and B3. And equation 4 says that B4 is some linear relation of B3, B3 and B2. And so on and so forth, right? So each equation basically expresses the ith as a linear equation of I minus first and I minus second, and so forth. And therefore, eventually, I'm going to find this as a linear equation of the initial two. Okay, so let's do that. 1 is 4 minus 3, that's this equation. And now I will use the next equation to express this thing as a linear combination. So this guy as a linear combination of these two, 4 and 23. Okay, so let's plug that in. So 3 is 23 minus 5 times 4. And you have to remember what are you looking for? What's the current B's? Like these are the guys, and this is just a coefficient. Okay, so I want to express 1 as a linear combination of 23 and 4. So I get minus 1 in here, and here I have 1 and a 5, minus 5. So how many 4s there are? 6. 1 in here and 5 here. All right. So now I go up, right? What's the next B to get rid of? It's this one. I can use equation 3, to express 4 as a linear combination of 23 and 27. All right, let's do that. So here's my 23, and now I express 4 as a linear combination of 27 and 23. And I do the algebra. So what is this? So this one is easy, 6. And this one is minus 6, minus 1, minus 7. Okay, so now I have 1 as a linear combination of 23 and 27 and 23. So let's go one level up. Let's express 23 as a linear combination of 77 and 27. That's equation 2. right? 23 as a linear combination of these. This is what we are moving here. So 23 I express as 77, linear combination of 77 and 27, these two. So it's 77 minus 227, right? That's what equation 2 said. So now let's group them. I have minus 7 in front of 77. And in front of 27, I had 6. And here I have minus 7 times minus 2. So that makes 14 plus 6, hence 20. Okay? And I'm almost done. Now I express this guy as a linear combination of these two. So now I need to use the fact that this guy is a linear combination of these two, and now will be done. One will be a linear combination of the initial ones, okay? So that's what I will do next. So I will try to drop this 27 thing using this equation as a linear combination of 258 and 77. So that's what I do. I copy this beginning, and I replace 27 as this. So now these are my B's. This is A and this is B. Okay, so 258, easy, it's just 20. And here what's going on? It's 20 times minus 3, so that's minus 60, and minus 7, so minus 7, 67. And always check, right? Check that answer, because like, who knows? There's too many plus minuses everywhere, right? So it is very easy to make a mistake in this stuff. So check, and then well, you know, if you made a mistake, then unfortunately you have to find it. So 20 times 258, well, you know, let's skip this algebra, but it's 5,160, right? A 0 immediate, and 2 times this is 16, 2 times 5 is 10, carry 1, so 11, and 2 times right is 4 with the carry 1, right? What about this? So this is, you know, this is 67 times 77. So okay, so I just did it like, what did I do? I think this is 77 times 7, right? 49, 4 carry, and again 49 plus 4, that's 53. Okay, and this is 462 is 77 times 6, right? So okay, so that's that, and I add the 2, it's 5,159, and so this is 1 plus that. So indeed, this minus this is exactly 1. Okay, and now, so we concluded with this equation. And now, what was the original question? Well, was what's 77? What's an inverse of 77 mod 258? Okay, so well, if you reduce mod 258, this thing drops out, and 1 stays 1, and this is what, minus 67 times 77. And it turns out, I mean, so basically an implication here is that minus 67 times 77 is 1 mod 258. And that means that whatever this thing was a multiplicative inverse of 77 mod 258, right? Because if I multiply the 2, I got a 1 mod 258, and that's because of this equation, right? So I could have answered that minus 67 is a multiplicative inverse, but I don't want to answer in this way, because I want to answer as some modular residue between 0 and 257, right? It's a mod 258. So, for example, for cryptography, if my, you know, I assume that my messages are encoded as integers, or my keys as integers. I don't want them to be negative. So, but that's easy, because minus 67 has a unique representation as a remainder mod 258, right? And it happens to be 191, all right? Because 67 plus 199 is 258. So this is the form of the answer that you should give. And, you know, I'm not going to bore you, but like you can verify this. And perhaps you should verify this. Although, you know, I guess at this point you don't have to. So you should have verified this equation. Okay. And once you do, then sort of there is no reason why there should be a mistake. But well, but I guess you can verify this, and you can multiply these two, and you get some large number. As you can see, I made plenty of mistakes myself checking this here, and whatever this number is 1 mod 258, because if I subtract 1, it actually divides. It's divisible by 258. So you can check that this is true as well, and that would imply this, and this would imply you know, this. Okay, and if somebody asks you, okay, what about multiplicative inverse of 258? 258 mod 77. Well, you can use the same equation to answer that question as well, right? So what is it? It's 20. Because if you reduce this mod 77, then this part drops out. This remains 1. And the consequence will be that 20 times 258 is 1 mod 77. And so therefore, the multiplicative inverse of 258 is 20 mod 77, because this times this will give you a 1 if I do mod 77 arithmetics. And you can check this as well, right? That the 258 times 20 minus is 1 plus something that is divisible by 77. So that something is 1 minus that, which is 5,159, and it does happen to be a multiple of 77. Okay, so thanks for listening. For whoever this was helpful, I hope that did help you. Okay, see you next time.